So Paul, we keep talking about dark matter and dark energy, and we should because they seem to be 95% of the universe. But it would be good to really understand how many atoms there are in the universe, since they're what we really know exists here on Earth. And we want to make sure we're not being led astray by underestimating how many atoms there are through, well, maybe it's some gamma ray gas or something we can't easily see. So it would be good to come up with a way to count how many atoms there are in the entire universe.
To count the normal matter, like the stuff we're made out of, as opposed to this exotic dark matter, whatever that is.
That's right.
And there is a way to do it, one we talked about briefly in the first course, which is primordial nucleosynthesis, if I can say that right. So this is the nuclear reactions that happened when the universe was very young. The basic idea is that between when the universe was about a minute and about 3 minutes old, the density and pressure everywhere in the universe are much higher than they are now, and they were about right to have fusion reactions going on across the entire universe.
Yeah, the conditions were analogous to what's going on in the center of our sun.
And the main reaction going on here is you take protons and neutrons and you combine them to form deuterium. And the deuterium doesn't last very long before something happens to it. It has a number of different pathways. It can go to form helium-3, or it can go to form lithium.
Yeah, deuterium, it turns out, is heavy hydrogen, as it's sometimes referred to in movies, but it is the least stable form. Well, I won't say the least stable form of hydrogen, but it's not very stable. It's very easy to convert into something else.
And there's only a very brief period when it's around. When it's early on, as we talked about in the first course, it's blown apart by the photons of what's now turned into the microwave background. But there is a window when they no longer have enough energy, and when it can go down these various reactions, and it moves rather rapidly to one of these things, and from thence it can go by many reactions to actually form helium.
Right.
And we know the universe ended up as roughly 20% helium and 80% hydrogen.
Yes, and most of the deuterium in the universe ends up being converted to helium, the helium that we see throughout the universe and in our balloons.
And that's what gives us a bit of a clue, because if you've got deuterium in the early universe and it's got anything else around, it's going to merge with that something else and go to helium. So there's a certain maximum possible density of deuterium you're going to get. If the density is any higher than that, it will collide, merge, end up as something else. So presumably you started off with more deuterium and everything went away until the remaining atoms of deuterium are so few and so far between that in the short period you've got before this whole reaction stops, they don't turn into anything else. So what that means is, almost independent of what you start off with, you're always going to end up with the same amount, same density of deuterium left over, because it's just whatever the density is when they're far enough apart that they won't collide or interact and get destroyed. And that's a very interesting sort of measurement stick. So the idea is, let's say you had a universe which had lots of baryons being protons, neutrons, anything like us, to begin with. And they're going to go through this nucleosynthesis stage, and they're going to turn into hydrogen and helium, and the standard amount of deuterium.
Yep.
Okay, so you're going to get a particular ratio. In this case, it's going to be a lot of hydrogen and helium to only a little amount of deuterium. But let's imagine instead you had fewer baryons to begin with. So you're now talking about a smaller number of baryons. Once again, it's going to go through the action, and it's going to turn into exactly the same amount of deuterium, which is as much deuterium as you can get away with, but it's just spread out enough so it can't destroy itself. But there's now going to be less left over. So what this means is, as you start off with fewer baryons, the ratio of deuterium to everything else is going to go up. Not because the amount of deuterium is changing, the deuterium density is always going to be the same, it's just there's less of everything else.
So this is a convenient little way to figure out how many baryons there are. It's a barometer, but not in the weather sense.
Yep. And so people can do these calculations, and this is nuclear physics that's pretty well understood because it's useful for killing people. And you get the deuterium to hydrogen ratio, which is pretty small, but somewhere between 10 to the minus 3 and 10 to the minus 6 on this graph. And you get photons per baryon. That's the actual number you get. We actually know the density of photons because we can measure them. They're in the microwave background today. And so this actually tells us how many baryons there were.
Right, and so all we have to do is being able to figure out how to measure how much deuterium there is in the universe. That should be easy. I can go into the ocean. The ocean's full of deuterium, Paul.
Well, yes, in principle. The trouble is that, of course, deuterium is also going to be either destroyed or created in nuclear reactions in stars going on subsequently. So if we look in the oceans, or we look on Earth, or look in the sun, we cannot be sure that the ratio of deuterium to hydrogen we see there is the same ratio it was to begin with.
Well, not only can we not be sure, we're almost sure it isn't the same because, for example, a star like the Sun destroys most of the deuterium throughout its lifetime. So,
Yeah, in fact, deuterium tends not to be created in stars, it tends to get destroyed because it's such an unstable thing. You put it in anywhere near nuclear fusion, it's going to get blown to pieces and turned into something else.
and so since we know that the Sun is about 1.4% metals, that is stuff not created in the Big Bang, we know there's been a lot of processing of that material. It's all mixed up. And so we really need to look at pristine material, stuff that, stars have not had a chance to chew through. And that's not so easy. There's not a lot of pristine material in the Milky Way, for example.
And this is one thing, again, we've talked about in the earlier parts of this course, the idea of trying to find the very first stars. If you can find a dwarf star that was one of the very first to form, just after the Big Bang, and didn't have any heavy elements in the gas cloud it formed, it will have produced some heavy elements and destroyed the deuterium in the centre. But for certain sorts of dwarf stars, there's no mixing between the surface and the outside. So the outer layers of the star should still, in principle, be nice and pristine and clear. And that's something that there's a lot of research on here at ANU. And no one's ever found a really pristine very first star, but they found some that aren't too far off. And you can try and measure deuterium in those.
It turns out not to be so easy because deuterium is a lot like hydrogen. It has this extra neutron in it, and so that neutron causes its energy levels to be shifted, it turns out, by a very small amount.
Yes, you're trying to look for an absorption line to deuterium that's right next door to an incredibly strong hydrogen line, because of course hydrogen is everywhere in huge amounts. So it's a very, very difficult task. And one place where it may be slightly easier is not in stars, but in intergalactic gas clouds. Once again, this is something we talked about a bit earlier in the course. The idea is if you look at a distant quasar or a distant gamma ray burst, as the light from it travels through space, every now and then it'll pass through a gas cloud and that will take a bite out of it. And this absorption line will mostly be due to hydrogen. These are called the Lyman alpha forest lines. And you can just read off the spectrum like a scroll. So yes, it went through gas here, gas there, gas there. But in principle, right next to the hydrogen line, you could see a much fainter deuterium line.
Yeah, and they have the advantage of not being, star has the problem where the gravity on a star is quite strong, and hydrogen lines get broadened pressure by the pressure, and so deuterium could be quite hard to measure in them.
So here it is actually possible, it has been measured. You're still not sure that these things absolutely are pristine. In fact, we know that many of these gas clouds do have some heavy elements in, so maybe it's the original number, maybe it isn't, but it probably gives us some estimate of what the original number is.
Well, we could certainly imagine going and looking at several of them and seeing, for example, you wouldn't expect the pristineness shouldn't always give the same answer. So it's worthwhile to go out and have a look at these and see if we get a consistent answer.
And this has been done, and it's telling us that the bulk of the dark matter cannot be in the form of baryons. So maybe it's about 30% of the universe is dark matter, but of that 30%, 25 has to be something that doesn't engage these nuclear reactions. And maybe about 4.5 or 5% is actually in the form of baryons, which is still a lot more than all the baryons we can see in stars. There must be some very hot, diffuse baryons out in deep intergalactic space that we can't easily see.
Yeah, so this number is consistent with about between 3.5 and I think 5% baryons of the universe is sort of the best number. And so that's consistent with this story of 95% of the universe being something else, because about 5% of the universe looks like it can be baryons by this method.
Okay, so now let's go on to perhaps the most powerful method of all, the microwave background lumps.